Welcome to the SE 410 video lecture on gear strength analysis. In class earlier, we've gone through gear kinematics, force, and speed analysis. We've talked in some detail about conjugate action and design of gear geometry to achieve a desired speed ratio. So in this video, we're going to look at gear failure due to yield and fatigue. In future videos, we're going to go through some worked examples and applications. So first question is, what loads are applied to gear teeth? Here we're looking specifically at spur gears, and you might recall that forces at the point of contact between teeth are normal to the tooth surface. Also, keep in mind that this point of contact moves as the teeth rotate. So what do gear tooth stress fields look like? Well, here we have two pair of gear teeth that are in contact. The contact point is at two different spots along the profile. And we can see in the case on the left, we have two areas of high stress. One is right where the teeth are in contact with each other, so we have this high surface contact stress. But then at the root fillet, we also have a high stress area, and that's due to bending. Due to bending, we need to pay attention to yield at the root fillet and also fatigue failure at the root fillet, which could occur at stress values much lower than yield strength. And at the contact surface, we should pay attention to surface pitting and wear, and this is primarily due to cyclic contact stresses and fatigue and material breaking off the surface. When we look at contact stresses, often we talk about Hertzian stresses, and this is a type of stress that can be calculated fairly easily for cylinders in contact. And if you want to get into more depth with contact mechanics and learn how do we actually derive these Hertzian stresses, there are courses and textbooks on contact mechanics that are available. Now, the load at the tip, if we have the contact point between two teeth at the tip of one of the teeth, that's going to give us a really large moment arm. But if our contact ratio is more than 1, on average, we're going to have more than one tooth in contact at a time. So that means we're going to have other teeth available to share the load. So even though we may have a really large moment arm, the load is reduced because we have other teeth sharing the load, and so that may not necessarily lead to the highest stresses when we have the contact point near the tip. So while the load is distributed across multiple teeth, the large moment arm does not lead to really high bending stresses because of the reduced force. So in other words, there's a trade-off between moment arm and force magnitude. And it turns out that wear tends to occur, pitting tends to occur where the pitch circle intersects the tooth surface. Something to keep in mind regarding fatigue is that there's no endurance limit for gears. So in other words, there's no infinite life, and we need to specify the number of cycles desired. Gear strength analysis really is a non-trivial topic. There are a lot of simplifications made in the textbook to make it easier to present. There's a much more complete reference, Dudley's Handbook on Gear Design, and it's very extensive and considers many different types of gears. In this course, we're limiting ourselves only to spur gear analysis. This is basically just getting your feet wet so you know what is involved with the analysis. But in the future, if you need to extend what you do with gear analysis or design, you'll need to refer to a more comprehensive reference. So gear strength background. This textbook begins with a really simplified historical model to help us understand the concepts behind models for gear stress. So we start off with a simple cantilever beam, and this helps us lead to the Lewis bending equations. And these also depend on what we call the transmitted and radial loads. And when we are calculating the stress at the root fillet due to bending, we're only looking at the transmitted load and not the radial load that would result in some compressive stresses. Okay, we're going to talk about the AGMA, the AGMA Stress Equations. This stands for the American Gear Manufacturers Association. They specify standards for gear design and manufacturing. The stress equations, when we look at the AGMA terminology, they use the term stress numbers, but in the textbook, the terminology differs a little bit to be more consistent with the rest of the textbook. So for these stress equations, there are different forms depending on what type of units you're using. In this video, we're only going to look at U.S. customary units. Later, we're going to compare stress against strength to determine safety factors. I'm going to present the equations, and then I'm going to step through each element in turn. So here's the bending stress equation, and then here is the contact stress equation that we need for predicting whether pitting is going to occur. So let's look first at the bending stress equation. We're going to step through each of these terms. This first factor is the transmitted load, which we defined just a moment ago. That's the force that is tangential to the gear tooth. The overload factor. This quantifies the effect due to torque fluctuations on stress. So for example, if we have an automotive engine with a four-stroke engine, we have fluctuations in torque due to the power cycle. This overload factor can be determined from a table in figure 14-17. If we have a uniform power source, this overload factor is simply 1. Now on to the dynamic factor. This accounts for inaccuracies in meshing. Now we've talked at length about the involute gear tooth geometry. This produces a constant speed ratio, but real gears are not perfect involutes. There is going to be some type of manufacturing error, and we can use the term transmission error to refer to the departure from a constant speed ratio. So what leads to transmission error? Geometric inaccuracy is a big one, and it's not just due to imperfect manufacturing, but also teeth wear. Sometimes there's plastic deformation. Even vibrations could cause problems. And high velocity can lead to greater transmission error. Dynamic unbalance, so if we have some kind of rotating eccentric mass or inertial coupling, then this could also lead to transmission error. Shaft misalignment, so recall when we were looking at constraints on shaft deflection at locations where gears are located. This is one reason why we want to make sure that the gears are aligned so that we can reduce transmission error. And we'll see later also there's some other effects if we have shaft misalignment. Tooth friction is another cause of transmission error. So how do we quantify transmission error? Let's look at what's called a quality number that indicates the level of quality or precision of manufacturing. So here is a typical range for commercial quality gears, but for high precision gears, the quality number is higher, between 8 and 12. So how do we calculate the dynamic factor? It depends both on the quality number and on the pitch line velocity, or the tangential translational velocity. So this is the formula for the pitch line velocity in terms of feet per second, where d sub p is the pinion pitch diameter, n sub p is the pinion rotational speed. And here we have the dynamic factor, and that depends on a few things in addition to the pitch line velocity. This quantity A, that depends on a quantity B, and B depends on the quality number. You can also go to figure 14-9 to see how for different quality numbers the dynamic factor changes as a function of pitch line velocity. One thing to observe here is that as we look at designs that have very high pitch line velocities, it becomes more important to use high quality gears. Let's look back again at the bending stress equation. We just finished looking at the dynamic factor. Now let's have a look at the size factor. This reflects non-uniform material properties due to size. So for example, if we think back to the section on spring design, uh, due to size, there was an effect on material properties. So there's not a specification in the AGMA specifications for size factor. There's basically just a placeholder there. And so they say to just use case of S equals 1 right now. But the textbook suggests that we can improve the accuracy of our model by thinking back to the section on fatigue, where there is a way of calculating the effect on fatigue performance as a function of size as far as how it differentiates from a standard rotating beam fatigue specimen. So remember, in calculating the size factor for fatigue, we look to find an equivalent diameter. And in this case, we have a cantilever beam. So what's the equivalent diameter for a cantilever beam, linking it back to the rotating beam polished specimen? So using that information from the earlier chapter on fatigue, we can build a more accurate model for the size factor, and that's equal to the formula that we have here, where F is the tooth face width. Recall what the tooth face width is, where Y is the Lewis form factor. So the Lewis bending equations, these are some of the historical equations the textbook goes through, and that's where this Lewis form factor is defined. It basically accounts for the geometry of the tooth. So y is equal to 2 times x times p divided by 3. So what are x and p? Well, going back to this diagram of a gear tooth, we can see what x is right here. It's a particular dimension, and there's a geometric relationship here that's needed for the Lewis bending equation. And x here is defined using similar triangles. That's equal to t squared divided by 4L. So this is related to the equivalent cantilever beam model, where t is the tooth thickness at the root and L is the cantilever length. So P, that's the diametral pitch, and that's equal to N, the number of teeth, divided by the pitch diameter. Okay, on to the next factor, pinion diametral pitch. Next factor, face width. We've already defined what that is. Case of M, the load distribution factor. This accounts for non-uniform distribution of load across the line of contact. So what is the line of contact? Here we have an image of both a helical gear tooth and a spur gear tooth. Let's focus on the spur gear tooth. When we have two teeth in contact, we don't contact over a wide patch, but it's really just a line of contact that contacts across the width of the tooth. So why might the load across the line of contact be uneven? Well, there are all sorts of things that can deflect. These are elastic components, not perfectly rigid. So the shaft can deflect, the gear itself can flex, the teeth can flex, and when these things flex, it can lead to a non-uniform load distribution across the tooth. And so that's what this load distribution factor is for, to account for this uneven load distribution. So how can we estimate this factor? There's an empirical formula available if certain conditions are met. If the ratio between the face width and the pinion pitch diameter is less than 2, we can use the following formula. Also, we are assuming that gears are mounted between bearings as opposed to on a cantilever section on a shaft. There's an upper limit on what the face width can be for this formula to work. And the line of contact, when under load, must span the entire width of the most narrow member, whether that's the pinion or the gear. This load distribution factor under these conditions is equal to the face load distribution factor, or C sub MF. And that's equal to the formula that we see here with a lot of factors that we now need to define. We're going to step through each of these terms now. C sub MC, this is a load correction factor. This depends on whether the teeth are crowned or not. So it's equal to 1 for uncrowned teeth and 0.8 for crowned teeth. And you might be wondering, what are crowned teeth? Well, when gears are misaligned, especially in the case of spur gears, we can have an increased load at the ends of the teeth instead of the center. And so one strategy for mitigating this issue is to crown the teeth, as shown in this diagram, where the thickness of the tooth actually gets a little bit smaller as we go out to the sides of the gear. This crowning can help decrease noise and vibration. Excessive crowning, however, leads to smaller contact lines and increased contact stress. So there is a design trade-off here. This next factor is the pinion proportion factor. This accounts for deflection due to load. It depends on face width and pitch diameter. There are 3 different cases depending on what range our face width is, and then we just use the appropriate formula, plugging in our values for face width and pitch diameter. The pinion proportion modifier, C sub PM, depends on where the gear is mounted on the shaft, or in other words, how close is it to the center. If you can imagine a shaft that's simply supported by 2 bearings, and if we have a gear right in the middle of it and we apply a load, that gear is going to stay fairly aligned with the axis of rotation. But if we have an offset from the center, then we're going to have some misalignment, and then this C sub PM is going to be something other than 1. So if it's right in the middle, then we're close to the middle, then C sub PM is equal to 1. If it's far enough away from the middle, then C sub PM is equal to 1.1. Using these quantities S1 and S, so what are those? Here's a diagram of a gear that's supported on a shaft between 2 bearings. S is the distance between the bearings, S over 2 is the midway point, and we're looking at how far away it is from the midpoint, S1, compared to the total distance between the bearings, S. Okay, now we're going back to the bending stress equation. We were looking at the load distribution factor, K sub M, and it's helpful along the way to think about, well, what design insights can we gain from going through these analysis models? Well, we would like, in general, to design for even load distribution to reduce the effects of stress. So one thing we could do is mount gears close to the shaft center so that we can have as close as possible to zero slope and better aligned gear teeth. The next factor is the rim thickness factor. If the material just below each tooth is compliant, it can bend, and this can affect fatigue. And we need to account for this reduced rigidity or increased compliance. So what exactly is the gear rim? Here's a rendering of a pinion and a gear. If we look at the larger gear, the gear, it has a reduced thickness as we go closer to the center. And below the teeth, where we have full thickness, that is the rim. And then we have this narrowing that's going to help us reduce the mass and reduce the cost of the gear. So here's the pinion, here's the gear. We only have full width part way below the teeth. That reduces thickness, saves mass and cost. If the rim is relatively thin, so the material just below the teeth, this is another source of compliance if the rim is not thick enough to essentially behave as a rigid body. So to get more precise, if we zoom in on the teeth and the rim, we can define the gear tooth hole depth as H sub t. and the rim thickness below the tooth as T sub r. And we can use that to predict whether we need to account for the account for a reduced gear rim thickness. So if the rim flexes and strains, then fatigue failure may actually occur in the rim instead of at the tooth root. So here's what fatigue failure may look like if we have a crack that propagates across the bottom of a tooth. But we can have different situations. So on the left of this diagram, figure A, this shows crack propagation through the tooth, and this is what we would expect if the rim is fairly rigid. But if the rim is less rigid, then the fatigue crack propagation could go through the rim instead, so more in a downward direction. So how do we calculate this? Well, if we have a thin rim, then we need to have a factor that's something other than 1. So it's 1.6 times the natural log of 2.242 over m sub b. And what is m sub b? M sub b is the ratio of the tooth and the rim thickness. And we can visualize this effect if we're looking at m sub b below 1.2 where we have a thin rim. This is where we would have an increased rim thickness factor k sub b, or in other words, as we move to the left on the plot below 1.2, k sub b increases. And if we move to the right, it just stays at a constant 1.0. So m sub b, we call that the backup ratio, and it's the ratio of the tooth thickness to the rim thickness. Back to the bending stress equation. The geometry factor for bending strength, or J, is what we're going to go through next. This accounts for the stress concentration at the root fillet. This is similar to the value, the quantity Y from the Lewis bending equation that accounts for tooth shape. Reducing J in this equation just by inspection will increase bending stress. And this is the final factor we're going to go through for calculating the bending stress equation. Remember, we still have, after this, the contact stress model to go through. Okay, J is equal to Y over K sub F times M sub N. So what are each of these quantities? Now, Y is not the Lewis form factor. This is another form factor defined by the AGMA. So keep that in mind. And K sub F, that's the stress concentration factor, and M sub N is the load sharing ratio. So the analysis for spur gears is more simple than for helical or other gear types. For spur gears, M sub N is simply 1.0. K sub F we can estimate using an empirical formula that was developed years ago based on photoelasticity experiments. You might wonder, what is photoelasticity? So these experiments use changes in optical properties due to mechanical deformation to help us determine what distributed strain properties are. So we're looking here at an image of two gears that are meshed with a load applied, and we can see both at the points of contact and also near the tooth root, there seems to be a lot more strain going on. Okay, back to calculating J. For this course, you can simply use figure 14-6 to obtain J, or J will be provided for you. This depends only, in this case, on tooth number ratios. Here's the figure. J is related to the load at the highest position of single tooth contact. And remember, as we reduce J, that increases bending stress. And that makes sense. If we're reducing the number of teeth in the mating gear, then we're going to end up increasing stress. Now, if we only had a single tooth in contact and the contact was occurring at the tip, J would be much lower and we would have a much higher stress value. You might be wondering what this diagram in the upper left is. This plot for J assumes certain properties for the generating rack geometry. So what is a generating rack? One possible strategy for machining a gear is to cut one using a generating rack. Here's the basic idea. If we have a particular shape, if we move it relative to the tooth that we're wanting to cut, the combination of all of these straight line cuts will add up to equal an involute profile. So how can we produce this particular type of motion? It turns out to be relatively straightforward. We can cut an involute by rotating a gear blank, a circular gear blank, as a cutting rack with a particular geometry moves back and forth out of plane, cutting metal away from the gear blank. So how does this happen? So here's another animation showing the cutting of a gear using a generating rack. So the generating rack is the straight rack with teeth, and then we have the circular gear blank. And what's not really shown here in the animation is we need to have some kind of movement out of plane, back and forth in and out of the screen, and that's where the cutting is actually going to occur. So here's a diagram of what it might actually look like if we were cutting a gear blank using this method. Now, we usually cannot cut all the way to full depth using a single pass with the generating rack, and so we cut just some at a time, and it requires multiple passes to go to full depth. Back to the bending stress equation. So in summary, we looked at this AGMA specification for predicting bending stress, and this needs to be compared against what's called the corrected bending strength to obtain the bending safety factor. And we reviewed how to calculate each one of these factors in this bending stress equation. The next steps here first are to look at the corrected bending strength calculation so we can get the safety factor, and then remember, we still have the contact stress and safety factor calculation to deal with. Okay, let's look at the bending strength and safety factor. So the safety factor is equal to the corrected bending strength divided by the bending stress. We just learned how to calculate the bending stress. Now we need to learn how to calculate the bending strength so we can get the safety factor. And then we're going to move on to the contact stress and safety factor calculation. Okay, let's look at each of these terms in turn. S sub t is the AGMA bending strength. This quantity is specific to gear analysis, so don't use this strength value for other types of applications. You can obtain this from these figures or from these tables. This quantity depends on the hardness of the gear, and this depends on how it's heat treated, is it hardened, and also what is the material made of, what kind of alloy is it, and it also depends on grade. So if we go to one of these figures, 14-4 in this case, this is an example of how S sub t varies with material alloy and Brinell hardness. Now, in case you don't know what Brinell hardness is, we should have a quick look at that. It's a standard measure of material indentation hardness. So imagine taking a very hard material in the shape of a sphere and applying a force to it and indenting a material that you're trying to test. So what we do is we apply a specified load, we note the diameter of the indenting sphere, and then we measure the indentation diameter, and with those quantities we can calculate what the Brinell hardness is. Okay, on to the next factor, stress cycle factor for bending stress. So remember, with gears, we don't have this infinite life property. So we always need to specify a particular number of load cycles, or N. The strength is based on a particular assumed life of 10 to the 7th load cycles. And if we have a speed ratio other than 1, we'll have a pinion and gear that are different sizes. And over the life of the gear set, the pinion, assuming it's smaller, it's going to have more cycles than the gear. So what if we have a number of cycles we want to design for other than 10 to the 7th? We need a modifying factor to account for a different fatigue life. And we've done similar things in the past in other sections of this class. So this factor depends on N, the number of load cycles, the material type, and the heat treatment. We can obtain this value from figure 14-14. So here's figure 14-14, and we can see how under different conditions for different materials, this factor varies with the number of load cycles. You can see from here that we don't have this flattening out like we did in the SN curve for steels. So in other words, we don't have an infinite life in this case. Okay, let's look at the next factor, the temperature factor. This accounts for reduced strength at high temperatures, but in this class we're just going to assume that this factor is 1. Reliability factor. Similar to how we calculate reliability for bearings, the gear strength values are based on a standard reliability level of 99%. So what if we want to design for a different reliability level? We need to adjust the strength accordingly, and we do that using the reliability factor. We can get this from table 14-10, or for other values, we can use the provided formula. So here's 14-10. We have these 5 discrete values of reliability, but if we need something other than those values, we can use the following formula. Before I get to that, just want to point out, it should be intuitive that if we want to increase the reliability requirement beyond 99%, that means we're going to have to increase K sub R, which will correspond then to reducing the predicted strength from the 99% reliability value. So if we have other values for reliability besides the 5 in table 14-10, we can use the following formula for K sub R depending on whether we are above or below 99% reliability. Okay, now we've covered all the factors required for the bending fatigue failure safety factor. And now we're going to look at contact stress failures. Let's look at contact stress and pitting failure. So in addition to bending stress at the root, surface pitting may occur at points of high contact stress, and we talked about earlier how this tends to be where the tooth surface intersects the pitch diameter. Here's an image of what happens when we have a root bending stress failure. Here's an image of what happens at the tooth flank when we have a pitting failure. And remember, this is due to fatigue. So we can see where the crack origins start, and the contact stress cycles cause crack propagation and eventually material to pit or chip off of the tooth surface. And here's a closer up view of pitting from a gear tooth. The contact stress can be estimated using Hertzian stress models for cylinders in contact. Here's the model for contact stress, and then the pitting failure safety factor. And we're going to go through each of these in turn and step through each of the quantities that you need to calculate. So just a note on determining the dominant failure mode, if we're looking at the safety factor for pitting versus the safety factor for bending, we actually need to use a trick here where we need to square the safety factor for pitting to make a fair comparison between these two safety factors due to some nonlinear properties. This is important if we want to be able to say which of these failure modes is going to be dominant. Now we're going to learn how to calculate contact stress. The first term is the elastic coefficient. This depends on the material properties of both the pinion and the gear. As you can see in the formula here, it depends on Poisson's ratio and Young's modulus for both the pinion and the gear. The next term is the transmitted load, which we've already reviewed. The next term is the overload factor, and this is the same as for the bending stress equation. The next is the dynamic factor, again, the same as for the bending stress equation. The size factor, also the same as for the bending stress equation. And the load distribution factor. So that speeds things up quite a bit, having already reviewed each of those factors. The next quantity is the pinion pitch diameter and the face width. So those two items are part of the geometric design of the gear set. The next factor is the surface condition factor. So this can account for different surface properties, whether those are detrimental or whether they enhance the pitting behavior of the gear teeth. And there are a lot of different things that could contribute to that. So rough machining or residual stresses, those would be detrimental, or maybe if we specify shot peening, that would induce beneficial compressive stresses that improve fatigue life. So in this course, unless it's specified otherwise, assume that this factor is 1. The next factor is the surface strength geometry factor. This is similar to the quantity J that we looked at for bending stress. This depends on pressure angle and speed ratio. This formula applies only to spur gears. For other gears, it's a little bit more complicated. Okay, now that we've learned how to calculate contact stress, let's look at the safety factor. There's the contact stress. We just reviewed that. S sub C is the allowable contact stress. We can obtain that from figure 14-5 or these tables. It requires a number of assumptions. First, that the number of load cycles is 10 to the 7th. Also, that we have unidirectional loading. What does unidirectional loading mean? Well, we only have for each rotation of the gear one loading of a tooth in the same direction. If we have instead an idler gear, for example, thinking back to our discussion on manual transmissions have an idler gear to reverse rotational direction. And if you imagine the rotation of an idler gear, it's going to go through two meshes and it's going to have bidirectional loading. Another assumption for this allowable contact stress is a reliability value of 99%. This depends on the alloy, the hardness of both the case and the core. So what does this mean, the hardness of the case and the core? This refers to something called case hardening. So here's a cross-section of a gear with a cutaway, and there are different types of heat treatments that can be performed for gears to improve their properties. And one of the options is to use case hardening. And this allows us to harden just the outer surface of the gear, and you can see that in this cutaway. The material near the surface is darker, the core is lighter, and the core and the case have different hardness values. So why would we want this? Well, if we have a harder case, then that's going to help us to prevent pitting and wear. But if we have a less hard core, then that's going to allow us to do a better job of absorbing shock as opposed to having brittle failure. So how do we get S sub C? We can look at figure 14-5, and that's going to depend on Brinell hardness and the grade of the material. Let's have a look at the next factor. This is the stress cycle factor for pitting resistance. We saw something similar in the bending stress or the bending strength calculations. We obtained this from figure 14-15. This accounts for load cycles that are different from 10 to the 7th. So here we can see, again, there's no infinite life behavior. And as we change the number of cycles, we can determine what z sub n is, and then that helps us to account for either fewer or more than 10 to the 7th load cycles. Okay, let's look at the hardness ratio factor. So we talked about case hardening as one option for heat treating a gear. Another option is through hardening, where we harden the entire gear. And we might choose to have different treatments for the pinion and gear. We might have different hardness values. Assuming that the pinion is smaller than the gear, the pinion will undergo more stress cycles than the gear. And so it may be desirable to have a pinion that is harder than the gear. So the calculations we're going to look at in just a moment here are for a specific case where a surface hardened pinion is mated to a through hardened gear. Now, what does this mean? Well, remember when we're talking about case hardening, if we only harden the outer surface and we allow the core to be less hard, it can do a better job with shock resistance. So it's resistant to brittle failure while still maintaining a really hard outer surface that's resistant to wear. Whereas if we had a through hardened gear, there's a limit on how hard we can make the gear. Otherwise, we would be risking brittle failure. So in other words, surface hardened gears are capable of higher hardness values than through hardened gears while still maintaining shock resistance because of the ductile core. So that's why we would want to surface harden the pinion and possibly through harden the gear. C sub h is used only for gear stress calculations. Leave it out of the calculation if you're looking at the pinion. How do we calculate it? It depends on two quantities, A prime and the speed ratio, m sub g. And there are three cases that depend on the ratio of the hardness to the pinion to the hardness of the gear. So if it's less than 1.2, this ratio, then A prime is 0. If it's within the range 1.2 to 1.7, we have this formula in the middle. And then if the ratio is high, above 1.7, it's 0.00698. Okay, in summary, we learned about two primary gear failure modes: yield and fatigue failure due to bending and also due to contact stresses. We learned how to calculate safety factors for both of these failure modes. We also provided a number of additional details to clarify some concepts that might not be entirely clear just from the textbooks. So for example, things like what are crown teeth? What do we mean exactly by rim thickness? What is case hardening? What are the deflections we might see due to uneven tooth loading? And there's some other things that we went through as well. So I hope that this video provides a good foundation for helping you analyze whether a particular gear set will fail and also to determine which failure mode may be dominant. And then I hope that you can build on this material and learn to extract some design insights from the information presented in this video. So for example, if we understand the failure modes, can we get some insight into how we should design things differently to avoid these failure modes? It would be ideal if we could design gears to guard against failure, but do it in an elegant way such that we can reduce cost, reduce mass, and reduce overall size of the gear set. That concludes this video. Thanks for your attention.